me.
All right, guys, let's get started. It's a new semester. We're excited today to kick it off with Tyler and Adam from Redpanda / Oxla, although Redpanda acquired Oxla last year, so that's pretty exciting. So Tyler is the CTO of Redpanda, and Adam was the CTO and creator of Oxla, and then now he's there you go, and now at Redpanda. So as always, if you have any questions for these guys as they're giving a talk, please feel free to unmute yourself and ask your question at any time. That way, they're not talking to themselves for an hour on Zoom. And if you can't speak, post your message on the chat, and I will interrupt on your behalf. Again, Tyler, Adam, thank you for kicking off the semester. The floor is yours. Go for it.
Awesome. Thank you, Andy. Really happy to be here. Really happy to have Adam Symanski with me as well.
Thank you.
We are going to do this in two parts. So I'm going to do the first part, which is sort of vaguely worded as why Oxla. So I'm going to give you a little bit of history of who we are at Redpanda, what we do, and kind of what led up to us acquiring Oxla, why we think Oxla is amazing, and how it fits into where we're going. And then, halfway-ish through, I'll hand over to Adam, and he's going to then do a deep dive on some Oxla internals, specifically the Hashmap implementation that they created. So who we are at Redpanda. So Redpanda has historically been a streaming data platform company. It started with a ground up C++ rewrite or implementation, I should say, not rewrite, implementation of a durable message queue, much like Apache Kafka, that was Apache Kafka compatible at the protocol layer. And we fuel mission critical data workloads the world over. Places like the New York Stock Exchange, the Olympics, all sorts of these kind of mission critical use cases run on top of Redpanda and really rely on kind of the core differentiators that have been in the product from day one around being simple, efficient, interoperable, and safe. And so we've always kind of focused on those. So that was kind of the core values that went into Redpanda day one, and that'll be relevant when we kind of talk about why Oxla was a good fit when I get down the line a little bit further, because it's sort of very much in the same vein as far as its attitude. The company's been around for 7 years, so we've gotten to the point where we've done a lot beyond just sort of core Kafka workloads. And you may have seen too, if you've sort of seen us in the news or poked around at our website, we are moving very heavily into the agentic space, which I'll talk a bit about as well. But we're not abandoning streaming either. We're sort of expanding beyond streaming and adding on top. So we've released a bunch of things like disaster recovery features this year, cloud topics. If you're familiar with WarpStream or these other implementations that allow you to basically do Kafka on cloud storage rather than Kafka on actual local disks. We have that as well. Effectively, an implementation that lets you do kind of any of the flavors of storage you want with the same brokers, kind of on a per topic basis, which is cool. Iceberg integration is another thing that we've done recently of just native export to Iceberg from within the brokers themselves. So it's just like the simplest, most turnkey solution you could have. You just turn it on and it just starts happening. It's super cool. We also, a couple of years ago, acquired a company called Benthos, which became Redpanda Connect, which is our connectivity platform. So it's kind of like 300 plus connectors to stream data in and stream data out. So this is this allows you to connect up your CDC streams or Snowflake or Databricks or things like that. Kind of all the different ways you might want to start pulling data in or pushing data out. And then I think the other key part of our platform that I want to highlight is that so we started out as a kind of self-hosted sort of thing, like single binary. Take the binary, you go run it however you want, knock yourself out, and super low ops, so really easy to use. But as with most companies, we've sort of moved into the cloud over time, and originally started out with kind of the dedicated cloud sort of offering as one might expect. But I think one of our key differentiators for the last couple of years has been our BYOC offering, which basically allows customers to have a managed version of Redpanda running in their private cloud VPC that we fully manage, but we have zero access to their data. So it's kind of the best of both worlds of, you can be in the cloud, you get this managed service experience, but with a very minor amount of kind of configuration and sharing of permissions. Basically, we get an account that has very scope permissions to kind of manage jobs that then reaches out to our control plane in order to kind of communicate. Other than that, there's hardly any changes that need to be made on the VPC side, and you can have these clusters that are run for you and run over your private data, and the data never has to leave your private network. So it's a super big differentiator for us from that perspective. As I mentioned, about a year ago, we started diving into the agentic AI space. We really see, I think Alex, our CEO, likens it to like, you think of the birth of the internet was kind of huge as far as the sort of shift it had on humans and human technology. AI obviously is in that same vein, but agentic AI in particular feels like this is sort of that next big opportunity, and we felt that this is a critical thing for us to potentially contribute to as a company. I'll admit, so I joined Redpanda shortly after the company had made the decision to head towards AI, and I'll admit I had joined despite the fact that they're heading towards AI, because I didn't want to get caught up in a company that was just kind of trying to ride the AI hype wave. But as we kind of dug into it and said, why isn't enterprise AI taking off like consumer AI is? We kind of sat down and cataloged, like, there's a bunch of things that you need to do in order to make AI successful in the enterprise. You need to build context and maintain it over time. You need to be able to query that context for agents to operate on. You need auth for identity and authorization so that you can enforce governance. You need auditing to be able to understand what these things are doing, because you can't debug them. You can't look and see, what is the if statement that made this thing do something stupid. It's this, organically grown model that just, is not only opaque, but also probabilistic. And so the only thing you can really do is kind of flight recorder style, record everything and analyze it post facto. And there's a whole bunch of stuff around routing and coordination, things like that. So we kind of looked at it and said, what are all these, logically, what are all the pieces that you really need to make enterprise AI happen? And it occurred to us that, like, a lot of these are actually data streaming problems, either naturally, or like governance isn't necessarily a data streaming problem by inherently, but in the realm of agents, where you're basically saying, I want to deploy a bunch of agents across my enterprise, and I want to connect them to all the data sources that we have, because if you want them to be your digital workforce, and just like your human workforce, so they're going to need to touch all of your private data in some way in aggregate. Having the streaming interconnect that they all communicate through be the place where we enforce governance actually ends up being a very natural way to do that. And so, this was kind of why for us it felt like, yes, we're actually in a really good place as a company to kind of help build out this type of infrastructure, because there's a bunch of it we do really well. It's a good foundation for governance. There's a bunch we need to build out. But then another piece of it, we did not have in our portfolio, and which is very non-trivial to build, is context querying. And of course, SQL querying isn't the only way that you or agents might query data, but it's a really super useful one. And agents are actually shockingly good at writing SQL. It's pretty fun. And so that's where Oxla came into the picture. And so last October, we acquired Oxla, which was, had basically spent, what was it, Adam, 5 years? 5 years building this super high performance distributed SQL engine. So it's an analytical database with a Postgres compatible wire format API on top of it. And yeah, it's a high performance analytical SQL engine. And that just ends up being a very useful thing to have in your portfolio. There's a ton of useful things you can do, especially if you can start pointing this thing at things like, I've got data that's coming in my Kafka topics. I want to be able to query that data. I've got data in Iceberg, or I've got data in other data stores that you can kind of plug into it. Having a high performance query engine that can sort of nimbly be deployed and utilized to query these resources is super valuable for humans and agents alike. The other thing that really drew us to Oxla was their focus on performance. We looked at a bunch of different companies out there, a bunch of different options. And, the first time I sat down and had a meeting with Adam, Like I was just grinning the entire time because he just kept diving into talking about like, well, we're doing this, then here's why we implemented it this way because we got to make sure that we're utilizing the cache lines effectively and we don't want to minimize cache misses. And like he's talking about all this sorts of stuff that we cared about deeply within Redpanda when we had built Redpanda, and today as we build it out further. And you could just tell this was someone who I was like, this is our people. Like these are our people. Like they speak our language. They do this the way that we want to do things. And so it just felt like a fantastic fit. And I had a lot of respect for kind of how they approached the problem of like looking at like, okay, if we're going to build a new analytical database from the ground up, like where are the bottlenecks now? And looking at the sort of the amount of CPU core count growth that has been happening versus the amount of memory bandwidth growth, and saying, there's basically a memory bandwidth bottleneck. That's kind of where a bunch of these key problems are, and how do we solve those over time? And so that was, one of the big design goals that went into Oxla from the beginning was, let's assume from a throughput perspective that this is kind of the world. Storage and network are approximately the same, and there's less, and they're sort of it's less important than memory and less important than compute. And so, taking that approach, they've really tackled various operators and various pieces of this system in ways that no one else has. And so the end result is, and of course, there's lies, damn lies, and there's benchmarks, but we'll sort of show you a few things here, and you can take them with all the grains of salt that you want. But I think the big takeaway for us was they built a really great system that can kind of play with the big players in the space. And of course, it always sort of depends on the specific use case, and Oxla is definitely a younger system than many of these, and so there are definitely missing pieces and things that we're not going out to try to compete against, as a full blown data warehouse, for example. Like I think that's just sort of beyond the what we would aim to do with this, but there are just super valuable places where being able to query things and plug this in becomes really important. One thing I did want to highlight, again, kind of hanging out in the benchmark space before I kind of wrap up and hand off to Alex, was we recently have been running some benchmarks. We've been working with NVIDIA. They've got this new Grace Hopper architecture coming out, which is basically like Grace is the CPU, Hopper is the GPU, and they have this really high interconnect between them. So actually lots of memory bandwidth, and also lots of cores. So the cores have, far more ability to communicate amongst themselves with the GPU and just in general access memory than sort of existing kind of classical architectures. And so we've been running a bunch of benchmarks and using like ClickHouse and the ClickBench, since they've got this really nice setup for kind of replicating benchmarks, which again, like it's a very narrow and specific type of benchmark. So take it with all the grains of salt that you want, but still an interesting sort of thing to look at. So we ran a bunch of tests at the sort of scale 100 size, and it's kind of super cool to see. I know this is kind of an eye chart, but the main takeaway is like on AWS, so this is like on classic x64 kind of architecture. Oxla is able to do better in a lot of cases, worse in some. There's a few queries specifically where it's like significantly faster. But I thought it was really fascinating then if you then move to the Grace Hopper architecture, where they have kind of basically allowed you to kind of scale up the number of cores and the amount of memory bandwidth communication between them. Oxla just does amazing on some of these, like the really ramps up. And I was kind of asking Adam why, and he might go into this more as part of it, although he said he could do a whole hour talk on this as well. But it sounds like a lot of it was because of the specific shuffle limitation that they have. They have one that kind of scales linearly with the number of cores really effectively. And so anyway, it's really cool to kind of see, when you approach systems programming from this perspective of like, how do I actually optimize for the various underlying hardware architecture pieces that get in the way, how you can really unlock a lot of performance.
I mean, maybe you guys are going to discuss this, but like this is the star schema benchmark, SSB, but this is are you just letting it generate whatever query plan at once, or like are they both generating the same query plan for some of these? Like are they going to have the same joiner? Like how much is the engine versus a crappy query plan?
So there certainly was, like on the, I think Adam can talk to the Oxla side. On the Oxla side, I think it's whatever it generates, and that's what the ClickHouse default is. And then the ClickHouse optimized one had some specific hints in it of like, here's sort of the join, the join orders or the partition information. And so that was like, in order to kind of optimize that better. But as far as I know, Oxla was just sort of out of the box.
Yeah, so no special settings in any kind of config, just the vanilla queries as they were provided in a paper of authors of SSB benchmark.
Got it. Thanks.
So actually, our observation was when we try to analyze like how people are using databases, even if you provide something that is extremely efficient, but people will not see these kind of results out of the box, they will actually do not see those results, because typically if you have a new database, when people start benchmarking several systems for the upcoming projects, they are not an experts. So they will make their decision based on the initial impression, right? Maybe they will spend 1 or 2 days on that, but if they will find a solution that works well out of the box, then they will go with that solution. So that was our focus, to have something that is efficient out of the box without any special tweaks or having some very specialized knowledge about our system, because how we can expect user to be expert in our system if you are new, right? So that was our assumption here.
Yeah. And that was another one of the sort of core values that really resonated with us at Redpanda. Is we'd always taken the same approach with Redpanda, of a lot of self-tuning, a lot of works well out of the box, and it just felt like a good fit. So all of that to say is, we acquired Oxla, and the desire then was that they're sort of being one more pillar of this agentic data plane that we're building, which is intended to kind of sit at the middle of your enterprise data, agents, and work across this span of self-hosted BYOC cloud, and really help bring agents to kind of to the enterprise. So hopefully that helps you sort of frame where Ox is coming from. And now the more interesting part of the talk, I'm going to hand off to Adam, and he's going to kind of deep dive into one of the specific aspects, the Hashmaps.
The part that, at least for me, is much more exciting, which is like the technical deep dive. I'll talk with you about something that became like the reason why I started working on Oxla. So I was analyzing why those existing systems at that time, when I started thinking about Oxla, when it was started my hobby project, I was looking on my stack based on Hadoop, and I was a bit disappointed with its performance. And I was analyzing why is this slow. So I started with the most popular operations when it comes to analytical databases, which is group by and join. Typically, if you have like lots of rows, millions, billions of rows, trillions of rows, you are doing some aggregation over that and maybe some joins before or after that, right? So those are the two most important operations for you. And they sound like something that is just have some hash map, you are doing lookup and doing some aggregation or joining two tables. So how hard it can be? Like, everybody knows hash maps, everybody's using them. So what's the issue? So to explain to you why it is not that trivial as it might seem on the first glance, let's think about something very, very simple when it comes to parallelization. Let's say that we have some workload in which each thread is performing completely separate work than other threads. Like no communication, no mutexes, no atomic variables. Each of threads is working on a separate part of memory. So no sharing of memory, anything, right? So we are simulating group by. We have a hash map in which we have key that is integer, value that is integer, and we have series generators that are, first series generator is generating the key, the second one is generating the value. And then we aggregate that. Okay, that's pretty simple. Let's see how does it perform. If we have a key generated of one of the 100 unique values, that's the performance I got on my computer, which has like 16 CPU cores. Pretty nice. It scales almost linearly, as we could expect. Pretty nice one, right? So what would happen if we increase number of unique keys? the results are all of a sudden completely different. As you can see, the throughput, even on a single thread, the throughput is all of a sudden like 10 times lower. And if we look on how does it scale, it just scales terribly. Like we are able to utilize like we have 1/4 of the throughput on all the cores compared to just a single core. So not only we have huge performance drop, we have also a very bad scaling of the performance. Why is that happening? Like we have the same code, right? We have the same amount of data, but all of a sudden the performance is completely different. Not only on a single core, but also scaling, while those threads are all independent from each other. So there must be something that those cores are sharing, which is of course the memory. And the memory is pretty complex thing. If you think about that from electronics perspective, we have these computing units like CPU cores, right? And we have to connect them somehow to each other to make them all see the same data, right? So typically in modern computer that have x86 architecture, we have three layers of cache. If we have ARM, it's typically two layers of cache. Some of the cache layers are shared, some of them are not. The architectures here are differing a lot between the manufacturers, between the generations of CPUs. And then we have a main memory. So whenever we try to write or read from memory, the request goes to L1 cache. If it's not present there, the given cache line, it goes to L2 or L3 and then to the main memory. And we are working on the minimal data exchange unit is cache line, which is typically 512 bytes of memory. Oh, sorry, bits. There is a mistake here. Sorry. And basically, the lower we go through this hierarchy, the slower it gets. And the difference is like 4 CPU clocks in L1 cache up to like over 100 CPU clock ticks when we call the main memory. And that's just scratching the surface. Like the memory itself is a very complex device, I would say, with lots of side effects that you have to take into account if you try to write something very efficient working in parallel. And as we have mentioned, the issue is that in the past, people were not thinking about this that much. When we had several cores, the memory was not a bottleneck. Of course, the cache was important because still it was introducing a huge latency, but the bandwidth was typically not limiting the performance that much as it's limiting right now. Nowadays, we have about 4 times lower memory bandwidth per instruction than we had like 10 years ago. So huge difference. And if we think about the hash maps, we have some a bit hard nut to crack if we think about that. So hash functions are based, hash maps are based on the hash functions. Good hash function is providing completely different values for even similar keys. And that means if we have a hash map that is large enough, almost every single lookup going into this hash map will result in a cache miss. And cache misses is something that we definitely want to avoid at any cost. So let's see how we can do that actually. By looking how we can do that, let's see on different kinds of hash maps. So first of all, one of the biggest differentiator is like the way of storing the data underneath, which is open addressing or separate chaining. In separate chaining, we have buckets. In each bucket, we have some data structure. It might be linked list. It might be linked list of buckets. It might be some kind of tree. And we can open addressing where the data is stored directly within an array. And if we have a separate structure underneath, that means more lookups into the memory. So that's not very good for the cache lookups. In the end, it results in a lot of cache misses. So in Oxla, we have decided to move on with open addressing and to have better locality. Then there are different ways of finding a bucket. And here, those strategies The goal of them is avoiding clustering. Of course, linear probing is resulting most likely in large clusters, but on the other hand, it's very good for the memory locality. So a bit counterintuitive. We would like to avoid clusters on the one hand, but on the other hand, it's good for cache locality. So that's why we have decided to use linear probing. Another issue with linear probing is how we handle removing the entries from the hash maps. It's pretty complex. You need to place tombstones in entries that you have removed. Luckily, if we are talking about our use case, which is group binds, joins, we do not have to remove any entries from the hash map. After we enter a new key, like as you have seen in our example, it stays there. So no need to implement deletes actually, which is pretty nice limitation for the problem that we are trying to solve.
Did you consider like for the I know you said you didn't implement the chain hashing, but like the Germans and I think DuckDB does this as well. They put it like basically a filter in the buckets on the bucket table so that when you probe, you can check the filter, see whether you even need to go into the chain itself. Did you consider that option? And there's other
Yes,
optimizations.
and we have something like that just on the next slide. The thing
Okay.
is that if you work on a group by, then typically, of course, it's not always the case, but typically the problem that people work on when they run aggregation is that they have typically more than single key no, more than single row for given key, right? Typically, you
Mhm.
have much more rows than you have a key. So typically, you know that the entry is most likely already there, but you have to find exactly where to update the aggregate. So
Got it.
that's not an issue typically. The issue is finding the proper place.
And then I mean, maybe you're getting this. Do you specialize your hash tables based on the data type, the way the ClickHouse guys do, or is it just one generic
Yes,
one?
yes, yes. There is a huge number of different types of algorithms we are using depending on the data type. Whether the key is something that has constant bit size, varying bit size, whether actual bit size of the key. There's different flavors of our hash map.
Okay, all
Here,
right. I'm stealing your thunder. Keep going.
yeah. Anyway, we try to focus in this presentation on something that we have in common between all those implementations and stuff that we think is pretty interesting. I think that some of you might have seen this optimization or different flavor of this optimization. We have, like in open addressing, an array containing key value pairs. But apart from that, we have separate array that contains a single byte prefix of hash. And those prefixes are aligned to 32 bytes. So thanks to that, we can quickly load this prefix using single simd load instruction, and then check whether the hash we are looking for, the probable matches with that. So that allows us finding the most probable position very fast. And we just do this once. So if we do not find the key here, it means it's not here. We are not going further in our hash map. That means that if we try to insert something and there is no free space within this 32 byte area, that means that we have to resize our hash map. So that's pretty tough. That means that our fill rate is not as high in some implementation that you can find in other places, but it is very fast. Like we have a strong upper bound of how long lookup will take time. So the zero means that the given bucket, given entry is empty. In case that the first byte of hash is zero, then we just change this to one. So we have like 2 times more entries for byte prefix one than for other prefixes, obviously. And then we check the matches, the position, we check actual key for the position with match. And that's actually pretty fast operation. But I think that the most interesting part in Oxla Hashmap is batching the lookups going to Hashmap, because we have a vectorized query engine, like most analytical databases nowadays. We can actually batch lookups going to the Hashmap. How does it work? So what we would like to achieve is that lookup that goes to the same region of memory should go one after another, right? To have the maximal probability that we will hit part of the cache that is hot. To do that, if we have a series of queries, each of them with some hash, then we put them into buckets. Of course, sorting would be better, but it's a bit too costly for this operation. So what we do is look on the upper n bits, typically it's 10 bits. And so that means that we have more or less 2 to the power of 10 buckets. We organize those incoming queries into those buckets, and then we run the lookup going from the first bucket to the last one. Actually, it's more like resorting those queries by that. So it's not actually going one by one through those buckets, but we have just first, we're organizing that in a way in which we have first queries for the bucket in growing order, as you can see on this slide on the bottom. So then we go through those queries and execute this on a hash map. That means that as long as the hash map is not really large, there is much less of cache misses than there would be otherwise. So that was something that contributed a lot to our performance. So it's like performing single step of radix sort. And it's kind of funny, counterintuitive, because if you remove that algorithm from our hash map, you get exactly the same result of your code. Your code is performing less instructions, but it's running slower, which is completely counterintuitive because typically what they teach us is that if you have less instructions, then it's faster, right? You have a better time complexity, right? There is smaller constant in your time complexity, which is typically something that people try to achieve. Here is otherwise, like the number of instructions you have to execute is bigger, and they are not changing the final result at all, but it's running faster thanks to this phase.
Right. So are you for this, like, are you when you say software prefetching, are you calling the instructions to prefetch or
No.
okay,
There's
okay.
So it's basically reorganizing. So then we are maximizing the chance that those queries that are addressing the same part of the memory are called one after another without evicting hot
Yeah.
part of the memory from the cache.
No, I understand. All right. No, we did work, it was a few years ago where like within the for loop, we would call prefetch instructions for the in the kernel, the next, iteration of the for loop. So the thing we wanted was there. But for this one, you're getting alignment benefits, I think is where you're getting way you're doing this. It's not, so it's prefetching, but not explicit prefetch instructions.
So the goal here was not, so prefetching is very nice if you want to improve performance on a single CPU core, but it will not minimize usage of memory bandwidth, right? You will have to load this data anyway. So it's just changing the moment in time in which you are loading something from the main memory to cache. What we are trying to achieve here is minimizing amount of load from the main memory. And if you have, let's say, 8,000 keys for which you want to perform lookup on your hash map, then if you perform those lookups in a random order, it will result in 8,000 lookups to some random places in memory, right?
Yes.
So that would result in some significant, so the hash map is large, each of those requests will go to completely different kind of memory. So even if there are two requests that would address the same part of memory, most likely the cache line that would get pulled for this second request will get evicted in between, right?
Yeah, I understand. Yeah, so it's not, you're not really prefetching. Like that's an
Yeah,
instruction. Right? It's like you're batching to get better
yeah.
reuse. I get it. Okay. I understand.
So it's about maximizing the chance of reusing the cache line. That's the
Yes.
goal here.
But yeah, but it says software prefetching, so that's why it triggered me. It was like, oh, is that?
Yes,
Yeah, I
yes,
understand.
yes.
I understand. I understand what you're doing. Thank you.
That's true.
Okay.
Another interesting thing is that if you think about joins, in joins we are using, of course, multi-maps, right? And in multi-maps, in case of SQL, when you perform join, of course, it might happen that we have several rows with the same key, but that's not the typical case. That people typically have a table that they are joining in which the keys are unique. That's the most typical use case. Nevertheless, the hash map must work correctly for both the case in which we have unique keys and non-unique keys. Some databases can provide user ability to hint that, okay, we expect at most one value for given key to use better optimized hash map, or they might store some statistics to handle this better. But what we do in Oxla is, I think, a bit different, and that's a trick I know from the game dev. So typically what you have in a multi-map is you have a key and then you have a pointer to some structure containing all the values for a given key. But if you have a pointer, the lowest bits of this pointer are always zeros because they are aligned to word size, right? So let's utilize this lowest byte. And what we do is that because the value for us is ID of the row with given key, so we know what we are storing in this multi-map. It's not like the general purpose multi-map. It's the map in which we have certain arbitrary key, but then the values is always unsigned 64-bit integer. Then what we do is, if we have actual pointer as a value to structure containing multiple values, then we have a 0. But if there is just a single value, then there is no point in having separate region of memory in which it lies, right? We can just put this instead of the pointer. But how to differentiate between the pointer and the value? By this least significant bit. So to extract actual value, what we do is we check the least significant bit. If it's 1, then we just shift the value by 1 bit, and then we return that. If it's 0, then okay, that means that we have some structure containing more of the values than just a single one. Simple, and yet it reduces number of unique cache lines that we are touching by one at every single request, which is a lot, actually. So that's like that 20-30% better memory, smaller memory throughput on joins, as long as they don't have a lot of rows for single key. And also we have a pretty funny optimization for the structure that contains those multiple values. Typically, what people are doing is chaining the buckets, which is nice, but it still requires jumping through the memory. Of course, if the bucket size fits well, the cache line, it's not hurting actual performance. Nevertheless, if you want to insert more values, it's not easy in time, that requires touching a lot of cache lines. And if you have a use case in which you have very few unique keys, but a lot of rows, then what is happening that at every single insertion, you are touching the end of the vector, and typically you have some data about the vector at the very beginning, and then the part to which you insert the data is at the very end of the vector, different part of the memory. And that's not good for your cache, right? And as you might have already realized, we are a bit obsessed about the cache lines and the cache. So what we do is, instead of storing a nice pointer to some descriptor and then cache to actual storage space, like in typical vector in C++, what we have is we are storing a pointer to place in array that contains the number of elements within an array. So as you can see here, we have like element 4 that have value 3. Let's say that, okay, we have an array that contains three values. Then if you want to iterate to check the list of the values for a given key, we just go left 3 times to obtain all those values. But if you want to perform insertion, what we do is we store the new value in the cell in which we have size, and we store the new size to the right. And then we update the pointer in a hash map pointing to this one cell on the right. And why is that important? So if we have like, I don't know, tens of thousands of unique keys, but billions of rows, then what we do is we store the new value in the cell in which we have size, and we store the new size to the right. And then we update the pointer in a hash map pointing to this one cell on the right. And why is that important? So whenever if we have like, I don't know, tens of thousands of unique keys, but billions of rows, then we need to store in a cache like 10, as many regions as we have unique keys, which is completely doable with tens of thousands of unique keys. So that means that each insertion is going to already hot part of the cache. And if the size is power of 2, that means that we have resize the whole vector. Luckily, we do not have to remove anything because it's joins and group bys, right? So no removal of any values. So we don't have to care about the performance of removing anything. And the last trick that you might also have seen in other places, nevertheless, it's pretty efficient. It's using Fibonacci numbers for sizes of the storage array. So if you're using power of 2, that is the most typical approach, a pretty reasonable one. If you, when it comes to like choosing how do you want to resize that. Using the power of 2 has a very nice benefits. It's very easy to calculate the position in an array. When you doing resizing, if you're using nice tricks, it doesn't mean that you always have to actually allocate the whole new part of the memory. If you're using this on the memory pages, you can just append more memory pages after the ones you have already. So something that ClickHouse is doing, very nice trick actually. That means that you will need to move like the half of your keys, key value pairs actually. And that's not a very nice property. But it's not very good in dispersing the clusters. And as you have seen, like the clusters are bad because that means that you need 8 or more steps to retrieve the value in classical hash maps, or in our case, clusters are causing us to have lower fill rate. To solve that, we are using Fibonacci numbers because then after the resizing, the keys are completely reshuffled through the array. They're typically not next to each other at all, because the greatest common denominator of subsequent Fibonacci numbers after a certain n value doesn't have anything in common, like, which is just amazing. But of course, the cost of the resize is higher than if you would use power of 2. The way we are alleviating this issue is that typically when we start building the hash maps for the join, we first try to estimate how big is the input for this hash map. Then we try to insert certain subset of the whole table to the hash map that we are going to build. Then we estimate how unique are the keys and how big will be the hash map in the end. We perform the resize for the final size of the hash map, and then we continue insertion. So thanks to that, there is no need to a lot of those costly resizing. Nevertheless, we do not have many clusters thanks to that. So that's more or less it. Thank you.
Okay, I will clap on behalf of the audience. Thank you so much. That was super interesting. Open up to anyone. If you want to ask questions, please feel free to unmute yourself and fire away at any time. There's a question in the chat. It says, do you guys share the same hash map between multiple queries? How do you know the data that feeds it is the same between queries?
So we do not have those estimates based on the previous query runs, but more like we can first start collecting the data for the join before we start inserting this into the hash map. Then when we start collecting this, if it grows over certain size, then we start shuffling this between the nodes if it's needed. But in the end, at some point, we are able to gather all the rows before we start building the hash map. So we know actual number of rows, and then we build hash map. So that's how we know how many rows will be there.
Yeah, sorry, it was actually my question. I was curious, like there was a slide where you explained how you rearrange the order of the queries depending on which region of the hash map they'll be hidden. And I got a little bit confused because I assumed that like each query would read its own files and then build its own like group by and stuff. Build its own hash map. But it seemed like you rearranged the order of the queries.
So we
based
are not
on.
rearranging the SQL queries. We are rearranging the queries to the hash map and the lookup
Oh, I see.
queries.
Okay,
To the
yeah,
hash
that
map.
makes sense.
All right. Anybody else?
Yeah, I think you made a really good point that cycles are essentially free compared to the memory bandwidth, and everything you're doing here helps a lot in terms of the memory bandwidth, especially when you're building these data structures. You presented some results on SSB. I was wondering how far are you in terms of looking at more complex queries, because sometimes the hash table cost is not always the biggest component. There's so much cost that goes in transferring data between the different operators. And also there are newer classes of methods where they might use Bloom filters and things like that to dramatically reduce what the hash table sizes are that you construct. So if you look at memory management as a whole for the entire query, uh, how much of this is contributing to the overall performance? And I know you are probably still experimenting with it, but we'd just like to get your thoughts on what does this look like in the grand scheme end to end for query processing?
Yeah. So typically, if we talk about what takes most of the time, apart from the memory, from the network communication and I/O, because of course that's typically pretty time consuming. So if the data is not cached, then the network bandwidth is dominating in the performance. But if we talk about the performance within the single node, then transformation that we are testing were only significant. It was something like regex or like operator. Otherwise, it was typically insignificant. Even operations like decompressing data, because we are caching compressed data, we are not decompressing this in cache. Even decompressing data is insignificant compared to hash maps. The reason behind that is that, yeah, CPU cycles are almost free. So the compressing of modern algorithms like ZSTD or LZ4, the context of those compression algorithms can fully fit into the cache, L1, L2 cache. If we talk about regex, they typically also fit into the cache and they typically perform very fast unless you have like very huge strings. And the rest, like adding numbers, dividing, multiplying, running some timestamp operations is typically very, very fast because it's like several instructions per row, which is much less than waiting 100 CPU clock ticks for the data in the main memory. Or
Great.
even worse if we have congestion on the bandwidth.
Yeah, makes sense. What you're doing, trying to get more out of the memory that you fetch from DRAM, totally makes sense. Nice work.
Actually, at some point, we got optimization that for certain query decreased number of instructions that we needed to execute by half for the whole query, which was just, so we expected like amazing performance gain. Actual performance gain was like 2 or 3% because this optimization was not minimizing amount of memory that we are pulling from the cache. So because number of cache misses stayed the same, it turned out that halving number of instructions haven't helped that much actually.
Thank you.
All right. Question the chat asks, and I'll piggyback off of this as well. How do you make sure that your cache doesn't get evicted by multiple running queries sharing a CPU? And then maybe before you get to answer that question, what is you mentioned it was a vectorized engine. Are you guys doing the morsel style scheduling? And then are you doing push or pull style query processing model?
So when it comes to query processing model, it's our own invention. It's like combination of push and pull that actually we have patented because it's something a bit different than what is typically being done. So we split the execution pipeline in what we call a single pipe. Pipe is starting with something that pulls and then tries to push. And we connect those pipes by channels, like the channels in Perl or Go. So and the channel has a buffer with depth of only one batch. So that means that given pipes start executing when it has some data to pull, but it will get blocked if the output channel is full. So there is no actual push-pull typical mechanism that you can see in other query engines.
Wait, so are you
So,
saying there's an intermediate buffer within the pipeline itself? Or are you saying
so
like,
you have a channel in between those pipes. So the pipe is the set of operations you can run without communication with anything else. And then if you need to communicate with other thread or other server within the cluster, then you use some kind of channel. If it's communication between CPU cores, you will use like the channel that like the one you can see in Go. If you want to communicate between the nodes, is like TCP/IP connection because it contains congestion control. So it's self-regulating system in that way.
so you start off pooling the data.
Yeah,
You're
for
just saying,
example, let's say we are starting by reading the data from Parquet file on S3, right?
mhm,
And then we want to aggregate that. But first we have something that reads, performs some transformation, like some projection, right? Then we have aggregation. Aggregation, depending on, maybe we have pre-aggregation because we have very few keys, right? So we can do all of that work within this thread. Maybe we need to do shuffle because we have lots of unique keys and they will not fit into the local hash map, right?
mhm,
So if we have to shuffle that or we need to shuffle the final aggregation result, then the pipe might get blocked because there will be nobody, because the consumer will be not fast enough for given pipe.
mhm,
And then there are those following pipes connected by those channels. So each of them has each pipe. So each stage has this pipe instantiated as many times as there are CPU cores. So we
mhm,
have lots of pipes at given time for at each server, like lots of them. And each of them are active all the time, as long as they have something to process.
mhm. Uh, I mean, it still smells like the push model, just you're blocking on inputs and outputs.
Yeah, kind of.
Okay.
So yeah, it's variation of that
Okay.
somehow.
All right. So then I think maybe that sort of answers the Bruno's question in the chat. Like, how do you make sure your cache doesn't get evicted by multiple running queries sharing a CPU? But in that case, like the pipes aren't going to help that because they have all data. Everyone has data. They just keep running. So I guess do anything special in that regard?
Actually, it's pretty nice because let's say that you have one pipe that is finishing what it was doing, and it's, for example, performing the shuffle, then collecting the whole bar that goes to another pipe on another CPU core, right? And there is like the clean handover. So it's pushing this to channel, and channel unlocks the consumer. So consumer is immediately starting to work on this batch that is in the cache, right? And that's what we want to achieve here.
Okay. But you allow multiple queries from different tenants or different, requests can run in parallel, correct?
Yes, they can, but right now what we do is actually that's one of the things we're working on right now. Typically what we try to achieve is that we are not sharing actual physical CPU cores between separate queries.
Got it. Okay. So
Then
that
the
that
then
got
you
it.
have this L1 cache locality fully utilized.
Got it. Okay, cool. I guess my last question would be what is your query optimizer implementation? Are you relying on Calcite or Orca or something outside, or did you write it yourself?
Oh, actually, that's the most disappointing part about our solution. We do not have optimizer yet.
Ah, okay.
So we have like a lot of like the optimization rules within the planner,
Yep.
but not based on actual data distribution, so not reorganizing, for example, joins yet.
So no cost-based search and any of that.
No, no, some of that is actually what's I think pretty interesting about our approach to controlling the flow of the data is that we can do a lot of that in a runtime within the query engine itself, not in a planner. So let's say that we have a group by operation. Most of the planners are deciding beforehand whether we do pre-aggregation or post-aggregation, right?
Hmm.
In case of Oxla, it's different. So we start always with pre-aggregation. So each thread is trying to do aggregation locally. And then it's observing after inserting another batch of data to the hash map, how it has grown. If it has grown over a certain size, that depends. This limit depends on the size of the L3 cache per core. If it grows beyond that, then we are shuffling those partial aggregations through the cores within the node, and then we check how unique were the keys. So how many we had unique keys and how many rows we have inserted. If we have more than 2 rows per key, then we continue doing this pre-aggregation. Otherwise, another batch that will come in will get shuffled through the node already instead of getting pre-aggregated. Then we have the same strategy within the node. We try to do so. Then each core has a certain subset of the keys, typical stuff, right? We try to do this aggregate locally. And then if we find out that, okay, this is also, our hash maps are not sufficient, even if you split that through the cores, then we switch to the strategy in which we do the shuffling through the whole cluster. So no matter what distribution of data you have, there is no risk that we will, have a bad guess in our planner about your data distribution and select the bad strategy. And typically, most of the planners are trying to are skewed towards selecting global shuffling and post-aggregate because there is a huge risk in doing pre-aggregate. If it will turn out that you have made mistake, your hash maps will grow, your memory consumption will explode, and the query will fail. So they tend to err on the side of doing pre-shuffling, post-aggregation. In our case, we start with different strategy, but nevertheless, it will not fail because of that, because then we will shuffle those hash maps, delete them, and that's it.
I mean, so not having an optimizer will get you through ClickBench or SSB, but like TBCDS, right? Anything when you need join order, like you guys basically can't handle that.
So with join orders, we also have a pretty nice ideas how to handle that, because what we could do with this streaming query, because our query engine, as you can imagine, those pipes is actually streaming data through that, right? So we have pipes and we have streams of batches going through them. And that means that we can actually have pretty nice estimates on the data coming from given pipe, because if you're reading data from Parquet file, then you can know exactly how many rows we'll get from this file, right? Then if you have, let's say, some filter, then you can, after pushing several batches through that, estimate how selective is given filter, right? So you can do estimate on size of the data that will get produced by this pipe. If you have group by, you do not need to actually produce the estimate of the size of the group by before you finish processing group by, right? Because nobody will be processing the partial output of group by later on, right? So you can do your group by and then say, okay, that many rows will get produced by this group by. With joins, it's a bit more complex. Joins may reduce amount of data, they may increase the amount of data. Nevertheless, like the filter, after pushing several batches, you can do the estimate. So we have also some ambitious plan to do the same kind of stuff like we have with group by, of selecting strategy for join, like reordering that. Because we can actually estimate size of each input of the given group of joins before we start processing the main bulk of data. We can just pull several batches for each input, then get estimate for each of those inputs, and then decide on the ordering in a runtime. So a bit different philosophy, I would say, than typically you would see on our query engines.
I mean, it sounds like you can do the one pass predicate transfer, but unless you can keep those pipes like do multiple passes on the same chunk of data, you may not be able to do Yanakakis.
No, we can just pull several batches to
Yes.
obtain this estimate, and that's it. So we store the several batches, I don't know, 4 or 5 batches, a single batch is 8,000 rows. So you can pull like 40,000 batches and see, okay, what's the estimate after that? What's the confidence of this estimate? You can actually obtain that. And then based on this, you can do this ordering after getting this sample of data.
Yeah. So you guys are planning to do Yanakakis.
Yeah, we are planning doing this. It's not
Okay.
done yet.
Of course.
I think it's pretty cool idea. I haven't seen anybody doing that. And I always, whenever you see some blog post saying, okay, we have increased performance of our query in Postgres or something 100 times, it's always how they have bypassed some kinds of mistakes in the planner.
Mm-hmm.
The assumption
Yes, of
planner is
course.
doing. It's the most typical performance issue people are observing in their workloads in most of the query engines. We would like to provide a new quality here.
Yep. Got it.
So I think it's a novel approach. I haven't seen that done before.
I mean, we're over time, but people have been. There's a lot of papers over the years, decades, of people trying to do adaptive query execution. Nobody's really built the full system and put it in production. So this is wild. This is interesting.